This is problem number 5 on the sample test problems for test number 2. Suppose that money is deposited into a bank account paying 4.5% interest compounded monthly. The balance T years after the initial deposit was made is given by B equals 5,000 times the quantity 1 plus 0.045 divided by 12, all to the 12t. A, what was the amount originally deposited? So some of you actually might recognize this formula, and it's okay if you don't, but this is looking like P times 1 plus R over N to the NT, where P is the principal and R is the annual interest rate, N is the number of times interest is compounded each year, and T is time. Now, it's okay if you don't know that, but for those of you who've seen it before, I just wanted to connect this formula to the one that you knew. And so actually that's why saying that the money is compounded monthly, that's why there's a 12 where the ends are. It's the number of times interest is compounded each year. You can see the 4.5%, that's the value of R. That's upstairs as a decimal. And then I guess that means that P is the number sitting here in front, it's 5,000. So if you happen to know the formula, then you know P stands for principal, and you know the answer is $5,000. But if you don't know that formula, what do you do? Well, the word originally means a particular moment in time. What value of T does the word originally correspond to? And it's T equals 0. So really what we want to do is just plug 0 in for the value of T and see what we get. 5,000, 1 plus 0.045 over 12 to the 12 times 0 equals 5,000 times all that, and then 12 times 0 is 0. But how much is anything to the 0? It's 1, so this is really 5,000 times 1, or simply 5,000. So that's the amount that was originally deposited. Part B, find dB dt and describe its meaning. Okay, before we do that, I would like to clean up our formula just a tiny bit. B equals 5,000. What I want to do is just get a decimal instead of writing all those fractions in there. So we'll type this in the calculator and get a decimal. So we're doing 1 plus 0.045 divided by 12. And we get 1.00375. So that's what goes in the parentheses. And that's still raised to the 12t. I just did that because I didn't want to write all those fractions every time. So now we want a derivative. dB dt equals. Okay, 5,000 is a constant multiple. Does it stay or go? Constant multiples stay. 5,000 times. Now we need a derivative rule. This thing right here sure looks like a number to the 12t. And that A is a constant. And so do we have a formula that looks an awful lot like a to the x? Do we have a formula for a to the x? We do. Derivative of a to the x is a to the x, copy that stuff just like it is, times ln of a, whatever a is. So that's the formula we're going to use here. So the derivative of this thing underlined in purple, 1.00375 to the 12t, that's like a to the x. So we copy it, a to the x, 1.00375 to the 12t, that's like the x, times ln of a. A is the number in the parentheses, so it's ln of 1.00375. And that would be the final answer, except this formula is only good if the power is x, if the power is simply the variable. But our power is a little more complicated than just x. Our power is like 12 times x. It's 12 times t. So what do you do when you have a derivative rule that applies just to an x, but you have something a little more complicated? Well, you follow the ordinary derivative rule like we did, but then you got to pay for it. And the chain rule comes in and says you got to multiply by the derivative of the stuff. Stuff is highlighted up there in yellow. The derivative of 12t is 12. So this is the derivative of 12t. So that's our answer for the derivative. Let's go ahead and clean it up. We've got a lot of constants floating around in the front, so let's mush them together. So we're going to type all this stuff in here. 5,000 times So 1.00375. And then why don't we just go ahead and multiply? Oh, that's silliness. That's not what I meant to do. 5,000 times. I can't grab that because it's to a power. It's the 12t. But I can multiply by the ln of this number. So let's insert the ln of that number. And then times the 12 at the end. And so we get, and this is dollars and cents. So we'll go ahead and just round it to the nearest penny. So 224.58. So that right there is our derivative. And we want to know what it means. So it's a derivative. It's an instantaneous rate of change. And the input is t. So at some moment in time t, the balance in our account is increasing at this rate, this thing that's in the black rectangle. So this gives the rate at which the balance is increasing. And we'll go ahead and include the units here. Okay, so the units for the derivative are just the units of the upstairs over the units of the downstairs. Upstairs was B, the units for B are dollars. Downstairs was T, units for T were years. I know it's compounded monthly, but T was measured in years. So the derivative gives the rate at which the balance is increasing in dollars per year at time T. You could also say it's the rate at which the money is growing, or the balance is growing at time t. And I know it's increasing and not decreasing because all that stuff in the black rectangle is positive. We know that exponential function is increasing the whole time. Part C, what is the rate of growth of the account balance when the money has been invested for 10 years? Include units. All right, I actually think we saved ourselves a little bit of work, or at least we did it a little bit early. So the units are dollars per year, and we just are looking for the value of the derivative. It's a growth rate. So this is dB dt. And it says when the money has been invested for 10 years. So our job is to just plug in t equals 10 into that blue formula up there. So we go 224.58, 1.00375 to the 12 times, and then this is the one spot where we make a change, 10. And so this is what we're after. So we'll type all that stuff in. And in fact, why don't we really use the good number, which is still stored there. So it's that number times 1.00375, close the parentheses, to the 12 times 10. Now I made a mistake here, and I'm hoping that you guys don't make that mistake. It's written 12 times 10. I typed it as 12 times 10. The problem is we need to put parentheses around the 12 times 10. We wrote it up there. That's how we knew it was a power, but the calculator doesn't know that. So you got to be really careful. Maybe better than getting into this mess of worrying about parentheses is to just type in a 120 instead of typing in 12 times 10. Either way, we should have our answer here, 351.91. And we want the units. Again, the units were dollars per year. So at the moment, when our money has been in the account for 10 years, the account balance is growing at $351.91 per year. Now, if you wait until the middle of that next year, then maybe your money is growing a little bit at a slightly faster rate. So we're not saying you're going to get exactly $351.91 in that 11th year, because this is just at the moment at the start of the 10th year, and it's growing, the rate itself is growing all the time. And I think that's it.